Now let's go into what I'm saying, okay? I'm saying this, okay? You got this guy moving, right? I'm saying that this light is moving at c plus v, okay? And you know why I'm saying that? I don't care what Einstein said. I'm not even thinking about Einstein. Only thing I'm thinking about is the universal law that doesn't change because the universe is like God. He tells us what the laws are. And we have only one law by him. And that's that space-time is relative to light at c. Okay? So if this guy is standing still and he has a clock like this, these people have a clock like this. So this guy, D, right? He has a clock like this, right? These people have a clock like this, right? So they are moving relative to space-time, okay? Now they can't shoot this gun out and it moves at c when they're moving at half c. That screws everything up, right? We said, and we proved that this is relative to space-time because over here, that's how we do our thing. If you move fast, what do we all say? Light has to move at 186,000 miles per second relative to this up and down thing, relative to space-time, right? Because what's it stretching from? Why are you making it go? You know, it's going through space more, right? So up here, obviously, according to the universal law, this light is moving at c minus v. This light is moving in the other direction, c plus v, meaning c 1.5 c, okay? Relative to space-time, okay? Now, relative to the two guys in the, A and C, so relative to space-time, they're both moving at c, right? We can't change that, man. We can't change that, right? Relative to this guy, right? Because we know it's relative to this up and down thing, right? Remember, because that's how time dilation works, right? So, relative to this, these lights, they have to go c, both directions, okay? Relative to this, which means this light, so this light has to go c minus the velocity, right? This one has to go c plus the velocity. So this light is moving 1 point c towards this guy, right? Relative to space-time, he's going c. And this way, he's going half c relative to everyone in this frame, right? But it's still going c. And so you might say, well, they're not going to agree on this guy when he got hit by the light. And I'm going to explain that, okay? And I'll explain why this isn't right where I say this is a Planck second. This is not a Planck second. A Planck second would be two of them. An up and a down. That's the thing where I got mixed up. And that will explain simultaneity, and will also explain when you flip your, if I knock this over so it was this way, right? So your photon clock was horizontal, instead of this way on this thing, right? Then your thing would be different. No one can figure out how that is. Oh, this explains everything. And then the Heisenberg uncertainty principle, explains it. But they didn't do it right. They didn't figure it out, right? Once you hear me, you will understand why we have that principle, the uncertainty principle. Everything will just fall into place. But this guy and this guy, they did their clocks, they were simultaneous, okay? All right? And light moved at c relative to space-time. Not to these people. To these people, this sped up and this slowed down, right? Before I go on to my, full explanation, let's go back to this lightning thing here, right? Lightning bolts come down, hit the ground at the same exact time. We'll just say the green light goes off. He says it's all simultaneous, right? Then we do it again, and a rocket ship comes by, and you can see the dotted line of the rocket ship in the back there, right? That's where the rocket used to be, right? He'd be lined up with this guy, right? The lightning bolts hit the ground exactly the same time, but, and he sees the same thing, right? But the guy in the spaceship, he's moving, right? So by the time the light gets to him, right, it's all going to look green like this, just like here. It'll go off in the same whatever, right? But since he's moving this way, when the light touches him, he's going to think it's compressed, but he's compressing it. He's the one turning it to blue light. Same over here. He is decompressing it. It'll be green the whole time until it catches up to him. But since he's, going away from the light, each one of these photons, he'll get slower and slower. So it gets red shifted and this gets blue shifted, right? It's not magic. It'll seem like, because he gets this stuff first, because he's going towards it, right? He'll seem like this is happening. The clock is like this, 10 after 3, and over here it's 3 o'clock. Like it's things are slow here and over. It's not that, and the length contraction. It's not, the universe didn't contract here, okay? The ship was moving, and the length in between here and here, used to be from here to here, right? Now it's only this line. So he contracted the length in between him and the photons. Not the universe didn't. The universe didn't contract itself. No, he did it. Okay. There's no different clocks. This lightning bolt and this lightning bolt, they don't have different clocks running slow and fast. No. Same up here. Okay. This guy, if you think that the clocks are running faster over there, that's because this is coming towards him. Just like over here, this is coming towards us, so it's faster. Over here, the photons are going away, so just like over here, the ship is going away, so it seems like it's slower. So they're taking this up to here. They're like flipping it and saying that it's true or whatever. Since this guy has a perception, it's real. No, it's not real. Okay, just like his length contraction isn't real. The time dilate isn't real. Okay. And the last thing is he can't see this guy. By the time these photons hit this guy's going to be way over here. He's going to be like, it's not possible to see, okay? So you don't have to worry about what he sees, okay? I say, though, that when he comes over here, they get hit, he gets to him, his brain will process it that they got that, and I'll explain why. But let's get that out of the way right now, though, until I'm done with my explanation. It doesn't matter what the hell he sees, because he ain't going to see nothing. He can't. This is moving too fast, and if it's moving slow enough for him to see, you don't have to worry about all this. You know what I mean? Because you won't feel the time dilation and this and that, because because of moving. You got to move really fast enough to where you can't. A stationary person ain't going to be able to see. Okay, but if this guy's stationary, he has a photon clock like this, going up and down, up and down. That's supposed to be a Planck second, going from here, one plate to the other, which is what I thought. Okay, but it's really going up and down. Okay, so let's get him out of the way first, right? We know he, relative to space-time, is standing still. Okay, so we know that the photons coming out of here are going C relative to this guy. Okay, if this guy was standing here, the photons are going C to him. Okay. And the photons this way, yeah, they're going C this way because he's standing still. So the photons are going C relative to him. That's not an Einstein law. That's a freaking universal law. We just saw the equations, man. Okay? Light moves C relative to space-time. Space, and he is relative to space-time is not moving. So relative to the photons, they are both moving. These ones are moving C that way, and these ones are moving C the other way. Okay? Light going to speed of C relative to space-time. We have it relative to he's perfect. He lines up with everything we say. Okay? Irrelevant what he sees or whatever, that's retarded. He can't see anything. Okay? But if he did see this coming first, it's because come on, it's the same reason here. The clocks didn't turn on Earth, and this one's running slow, and this is running fast. Same way up here. It's just your perception, man. But so we got the green guy. He meets our rules for not Einstein's thing, but for and Einstein, both Einstein and the universal thing. Right? So let's look at let's do the blue guy. The blue guy is going to come out at 1.5 C, right? relative to this frame, right? So it's going to come at this guy like quick, right? Really quick. Right? But they're moving this way relative to that. So the lights are going to be spread out, right? The photons that come out. Because as they come out, he's going to be moving the opposite way, and then another photon, then he moves more, and another photon. It's going to get spread out, right? Over here, it's going to do the opposite, right? It's going to be all condensed. Every photon he puts out, the next one, he's moving along with that photon. So he's compressing them, right? So the blue guy is going to shoot out his photons, right? They're going at 1.5 C relative to this frame, right? So it's going to hit him. Look at this little arrow. That's the arrow representing going this way, right? So it hits the black man, right, at this little tiny bit of whatever, right? It only had to go a little bit of tiny way because they're moving in the opposite direction, right? But this man right here, he doesn't know when this guy gets hit with the photons. He doesn't have ESP or anything like that, right? He has to wait for the photons to bounce back to him, right? And as we know, if that happened, the compression, right, would cancel out, right? Because if this whole frame is whatever, this would cancel out on its way back. And it would be compressed like this, right? And it would take longer time to get back to him. And if you did the math and you figured it out, this two-way travel, okay, this two-way travel would be 1c, okay? To the blue guy, he would think, you know, that light traveled at c, even though one way it went 1.5 c relative to him, and the other way it went 1/2 c relative to him. It adds up to, 2c divided by 2, because it was a two-way trip, adds up to c, right? The compression gets canceled out on its way back, right? Let's say they're sending out green photons, right? As it goes out, he's gonna like decompress it, right? So it'll get less and less. It'll get more red shifted, right? It hits whatever, this guy, right? It bounces back. But as it comes back, now it is blue shifted in the same exact rate, right? So he gets the same color back, green, and he gets the same time. Now, think of this guy, okay? This all has to do with two-way speed of light. This is why in the Planck length, or the Planck second, this all has to do with this. This is why you can't look beyond the Planck length or a Planck second, because the physics won't let you. Okay. Now, this red man, okay, he's going to send out some photons, right? And they're going to go 1/2 c compared to his frame, right? So it's going to take forever to get up to the black man, right? And it's going to be compressed, right? So every photon he puts out, he's moving along with that photon and putting out another photon, and they're all getting compressed, okay? But let's say this is green he puts out, right? And by the time it gets up to here, it's compressed and it looks blue or whatever. But when it bounces back, this Doppler effect is canceled out if they go constant speed. That's a fact, okay? Now, so it'll take this long to whatever to get to the black man, but to get back to the red man, he can only add up these two lines, just like the blue man. He can only add up these two lines. He can't know when the light hit him. All he can know is when the light hit him and came back. How long was that? Same with the red guy. He can't know ever when this guy got hit with his photons, but he can know when the photons hit him and came back. He can know the two-way. He cannot know the two-way thing. Physics doesn't rely on this being 1 second. Physics relies on this being 1 second, right? When you have your clock longitude like that, that's why you need two of them. Like say this blue line and this red line. Here's a whole line.